In this video, we're going to look at how to solve rate law problems for reactions that have more than one reactant. The obvious problem that this presents is if we increase both of our reactants' concentrations, how do we know which of these concentrations is having an effect on the rate? And moreover, how do we know what the order of magnitude relationship is between each of the concentrations and the rate if we're changing two concentrations at a time? The obvious answer is we can't. So the simple solution is to do the experiment twice over, but in each experiment, keep the concentrations of a different reactant constant so that we are only changing one reactant's concentrations. So in this first set of data, we see that our concentration of nitrogen monoxide remains constant at 0.10 moles per liter, and therefore it's hydrogen gases concentration that is the variable, and vice versa for the second data set here. From this, our determination of reaction order is done in exactly the same way. So let's start by determining hydrogen gases reaction order by comparing experiment data for experiments 1 and 2. So let's start by simply dividing the concentrations used in experiment 1 and experiment 2, and obviously we can see that we doubled the concentration from reaction 1 to reaction 2, and now we just need to figure out what the order of magnitude relationship is between the concentration and the rate. So if we take our rates, which are exactly the same as the concentrations, sans the units, we see that a doubling of the concentration results in a doubling of the rate. This is a fairly simple one-to-one relationship, meaning that 2 to the exponent n is equal to 2, therefore n must equal 1, and we have a direct linear relationship between the concentration of H2 and the increase in reaction rate, meaning that we can write out our rate law by writing rate is equal to K, the constant that represents the effective temperature, times the concentration of hydrogen gas to the exponent 1. All that we have left to do is to calculate the order of magnitude for nitrogen monoxide. So let's go ahead and compare experiment data 1 and experiment data 2 exactly the same way as we did with hydrogen gas. So if we do that, we find that our two experiments involved a doubling, once again, of the concentration. And again, we want to know what the relationship is with the concentration and the rate. So if we look at the change in rates, we see that a doubling in concentration resulted in a fourfold increase in the rate, meaning that 2 to the exponent n is equal to 4, meaning that n must be equal to 2, which means that we have a quadratic relationship between concentration increases and the resulting rate increases that occur, meaning that we can write our rate law in its entirety this time by adding concentration of nitrogen monoxide to the exponent 2, meaning that nitrogen monoxide has a second order of magnitude relationship with the rate. Now that we have our complete rate law, we can talk about the overall reaction order, which means by what order of magnitude do the concentration of both of our reactants affect the rate. And to find this out, we simply take the sum of the individual orders of magnitude of our reactants. So we know that the order of magnitude of hydrogen gases concentration is 1, and we add to that the order of magnitude of nitrogen monoxide's concentration, which is 2, meaning that we have a third order reaction order overall, meaning that there is a cubic relationship between all of our reactants' concentration and the overall reaction rate. All that remains is to calculate what the magnitude of K is, and fortunately all we need to do is substitute some data in. So we're going to use the data from experiment 1 because the numbers for both of the concentrations and the rate in moles per liter per second are the same number, 0.10. So if we write this out, our rate is 0.10 moles per liter per second, which is equal to K times the concentration of hydrogen gas, which is 0.10 moles per liter, and times the concentration of nitrogen monoxide, which is 0.10 moles per liter, squared. So if we move everything over so that we can isolate K, what we're going to do is divide both sides by our concentration, which would mean that K is equal to our rate, 0.10 moles per liter per second, divided by 0.10 moles per liter times 0.10, let's get the units in there, moles per liter squared. Now we can see that we can actually solve this without using a calculator here, so we can see that 0.1 in the numerator and 0.1 in the denominator cancel each other out. We also have moles per liter up here and moles per liter down here, which cancel each other out as well, meaning that we can simplify this equation by simply writing 1 unit with the units 1 over seconds here, because moles per liter cancel itself out. And if you do 0.1 times 0.1, you would get 0.010 moles per liter squared, and 1 divided by 0.01 is the same as 1 over 100, which, if you put it into your calculator, is simply 100, and with the proper units, divided by seconds over moles per liter, or moles per liter squared. So again, the units don't really mean anything on their own. Remember that these particular units just exist to make sure that all of our other units balance out, and that allows this equation to be true. So again, this number that we've calculated is the relationship that temperature has to the equation, independent of concentration. So if we write our complete rate law, we can say that rate is equal to 100 times the concentration of H2 times the concentration of nitrogen monoxide squared. And that concludes our videos on rate law. Remember how rate laws are constructed, because rate laws are the foundation of another mathematical relationship that we're going to talk about when we begin to talk about chemical equilibrium systems.